Okay, so in this video I'm going to talk about Fourier integral, and we are going to continue on Fourier concept in general. Before we have discussed about Fourier series, and in this video we are going to talk about Fourier integral. Okay, so now let's jump directly to an introduction to Fourier integral. If we have a function which is f of x that is defined on a minus L to L interval, that this interval is like between, as we said, minus L to L, so that we are between the positive and negative range, okay, and they are the same, minus L and L. We may be able to represent this function, which is f of x, as a Fourier series. This is already we have understood before and we have explained before. Okay, we can represent any function, okay, between this interval as a Fourier series, okay, on this interval. However, Fourier series are tied to intervals. That's the issue, okay. Intervals means that, as we said, from minus L to L. This is why I was like placing emphasis upon minus L to L here. So this means that we are dealing with a specific period or interval. But what if that we want to define the function, this function, over the entire line? That is something that is going, okay, from here and here. What we are going to do? Okay, so if this function that we are dealing with, f of x, is defined over the entire line and is not periodic, it's not repetitive, okay, it doesn't have a repetitive pattern, then the idea of a Fourier series representation is going to be replaced with the idea of, exactly, Fourier integral representation. This means that we are going to change what we used to have, which is the summation. You remember, from n equal to 0 to infinity, because this is like discrete elements. Like we're taking some like terms, that is counted terms, but we are going to change it to what exactly? An integration from 0 to infinity, okay. So this is what we are going to deal with, and this is what is the meaning of Fourier integration. Okay, let's clean. Assume that this function f is absolutely integrable. Let's assume that this is integrable. This is like some assumptions, which means that the meaning of integrable, absolutely integrable, that the integration of this function from minus infinity to infinity, absolute integration of this, the integration of the absolute value of this function, okay, dx, converges. Converge means that it has a value, okay, it converges to a specific value, okay. We also assume that f is piecewise smooth, and I think that you understand now what is the meaning of piecewise smooth. We are repeating it every time. If you do not understand them, please refer to the previous videos, okay. So in every interval minus L to L, okay, then we are going to define something later. Just consider now that I'm going to like have some like parameters from our function and put it together and represent it with something called omega n, a new parameter, okay. So consider that n times pi over L, okay, it equals to omega n, okay. This is only something that we're going to use later. Okay, so now let's define our Fourier integral of our function, which is f of x, on what exactly? We're talking now about real line. It's not interval anymore, okay. And it has the form. What is the form now? It is going to be the integration from 0 to infinity, okay, of what? A omega cosine omega x plus b omega sine omega x d omega. So now there is something a little bit different than what we have used before. There's something called omega here. Yes, this is the like the integration, or the this is what we call it, the integration variable, the new one, okay. We're going to see that it is going, the integration or Fourier integral is going to introduce this omega, okay, the concept of omega, another integration variable that we didn't use before, and we are going to get benefit from this later on, as we are going to see later on, like Fourier transform, that we are going to change our variable from like one variable like t, for example, time domain, to something else like frequency, which is going to be frequency domain. Okay, so this is what Fourier integral is all about, and we are going to see this and discover this in a minute. In which Fourier integral coefficients, I mean that a omega, b omega, well, are going to be interpreted or are going to be defined as 1 over pi minus from minus infinity to infinity f of z cosine omega z dz. Okay, so this is the integration that we are going to use in order to define a omega, which is the integral coefficient here, and this is b omega. We're going to find also it equals to 1 over pi from minus infinity to infinity, okay, f of z, but here we're talking about sine, not cosine as here, okay, sine omega z dz. So they are almost identical, okay, almost identical, except that we are using here cosine and here we are using sine. Okay, so now we can have some remarks on this. The integration variable, that is, which is omega, that we have mentioned before, replaces the summation index. And do you remember that we were like having this n equal to 0 from n equal to 0 to infinity or a certain number? So now this kind of variable, we call it the summation index, is replaced by omega as the integration variable omega. Okay, okay, in this, so it is pretty similar to what we have said before. Okay, just we were using discrete summation before, now we are using integration like a continuous function. As with Fourier series, the relationship between the integral, okay, which is 14.1, which is this integral, okay, and f of x must be clarified. Do you remember that I have mentioned about this before? Whenever that in Fourier series, if you remember, that we need to define what is Fourier series or integral in this part going to be related to our function. Means that what is the convergence here? How the meaning here is that if we have, let's clean something, if we have a function like this, for example, okay, then our Fourier series is going to be like something like this. So at the end, we are highly interested with the end, okay, at the ends here and here. What is the convergence of our Fourier series? It might be something like this, it might be something like this, okay, and then come back here. So we are going to have a convergence, for example, something like this. And in between, we also want to see how this Fourier series is going to represent our function. Our function is a smooth one, and Fourier series is something like this. So we want to see what is the convergence of our Fourier series at any part on the function, on our interval. We were talking about interval before in Fourier series, okay, but here we are talking about real line. So we want to know this. We want to put the function, or we want to put the theorem of convergence between the integral, Fourier integral, and our function. Okay, so now we are ready to the next step, which is theorem 14.1. We are going to use it later, which is what exactly? The convergence. That's the issue. Okay, that's the issue. The convergence of the Fourier integral. Okay, we're going to find that if we have a function which is f of x, okay, and it is defined for all real x, okay, we're talking about real x now, on that we have this integral, as we said, absolutely integrable, okay, from minus infinity to infinity, f of x, okay, and this is the absolute value of f of x, dx converges. We must say that. We must say that in the beginning. We must state that in the beginning, that f of x is defined for all real x and that it is absolutely integrable. Okay. Suppose f is piecewise. Do you remember piecewise again? Smooth means that the derivation of it is going to be piecewise as well on every interval minus L to L for this part. So which is, if we have a function here, we have minus L, we have minus L here, and we have LE. So we are saying that if it's piecewise between minus L and L, okay, for L larger than 0, this means that we have 0 here, L is positive, okay, larger than 0, okay. These are like the conditions that we are going to state our convergence theorem based upon, okay. Then at any x here, this is x, at any x, the Fourier integral, which is already we have done before, this is 14.1, this is our Fourier integral, a omega cosine, b omega sine, okay. The Fourier integral of the function f converges to what? Exactly. You can tell it because you have already you've gone through this before, right? It's similar to the Fourier series. Actually, it's identical. Half of f of x from the right, we said that before, this is right, and plus f of x from the left. So here this is right from the right and from left, right? Do you remember we said that before? If we have a function, we have something that is at a particular point here. This is f of x coming from the right, and here this is f of x coming from the left, right? Converging to what? Converging to f of x. This is f of x, right? So when we are telling that we are going to say that our Fourier integral is going to converge to half of the value of the function at x approaching it from right plus the value of the function at x approaching it from the left. Okay, so this is the meaning of the convergence theorem. Okay, now we are ready for what we call it the example, and I'm going to end up here, and then I'm going to make another video for the example.